perpendicular over tension. Megan, could you rewrite this and get tension perpendicular by itself? Okay. T sine 40 times 3. What are they wanting us to find in this question? What if they asked for the weight? What are they asking me to find? mg. I did that to you guys, I think, on your unit test on this unit. It doesn't show up very often, but that's just like cheap marks. Don't throw that away. Read the question carefully. So it looks like here the mass is going to be the tension times the sine of 40 times 3 divided by the sine of 65 times 2. Tension was 150 times g. Thank you. Tension was 150. Sine 40, 3 divided by sine 65 times 2 times 9.8. Don't need to do negative 9.8. We took care of the in our torques. We took care of the negatives. Make sure I'm in degrees. I am. 150 sine 40 times 3 divided by, this has to be in brackets, sine 65, close bracket, times 2 times 9.8, close bracket. Did I miss anything? 150 sine 40. By the way, why don't I have to put this in brackets? Your calculator assumes things are on the top if you don't tell it specifically, right? I'm getting 16.3 kilograms. Jesse. Okay. Center of mass is weird, but yeah, well, here you go. Here's another one that shows up. I'm just going to get this one started, and then we'll talk about this. Can I get? Yeah, I can get it all on one page. The ladder question. In fact, I think in your notes I called this the famous ladder problem. They want us to find the minimum force of friction between the ladder and the floor that's required to keep the ladder from sliding. Okay. Let's list all of the forces on this ladder. Get the obvious ones. Okay, we have the mass of the ladder. Let's see. The ladder is 5 meters, so the mass of the ladder would be right about here. I'll call it mass of the ladder times g. And then we also have the mass of the person. I won't draw it quite that big. Mass of the person times g. We would also have a normal force right there, because it's touching a wall, it's leaning against the wall, so the wall will push back. There will also be a normal force right here. So you know what I'm going to do? I'll call this normal force number 1, because it's the one from the floor that we're used to. I'll call this, instead of normal force, I'm going to make the N into a W. I'll call it force of the wall. This can't possibly be it.
Sorry to interrupt classes, but we have a blue Caravan parked in the back parking lot that is blocking the access. License JJF182. If you could go out immediately and move it. The blue Caravan in the back parking lot, JJF182.
Force of the wall. Christina, what direction is this force? Are there any other forces to the right? Then this ladder would have to be accelerating. Ah, wait a minute. I think friction is that way. Not only that, I think normal force number 1 cancels out the mass of the person times g and the mass of the ladder times g. and the force of the wall equals friction. To do this question, we would go components, use torques to find this. Once you know that, you know force of the wall, and that's friction. In other words, even though this question is saying find the minimum force of friction, you're not. You're going to find the force of the wall, which is friction. Okay? Problem is, this question would take me about 10 minutes, and I haven't got that much time. We did a couple like that in your homework. If you look, the lesson was called the famous ladder problem. I think it was lesson 4 of equilibrium, something like that. Momentum. Whoop, wrong button. A curling stone is sliding along the ice when it hits a stationary 15-kilogram bucket of sand. After the collision, the curling stone's velocity is 3 meters per second east. I better draw a compass. And the bucket has a velocity of 22 meters per second, 40 degrees south of east. What direction was the curling stone moving before the collision? So this is a collision. Collision, momentum. Let me say this again. Collision, momentum. I'm going to say this one more time. Hint, hint, hint. Collision, momentum. Hopefully you'll remember that in a couple of days. Okay? And here's what we said. The sum of all of the initial momentum, the sum of the momentum before the collision, was the same as the sum of the momentum after the collision. Unfortunately, this was not like energy, where you went also kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. Those were scalars. Those you could solve by doing straight math and cross multiplying, and you were done. These, momentum is a vector. We're going to carefully draw pictures. After the collision, what do I have moving? Curling stone, which way? So I'm going to draw that like this. There's the curling stone. How much momentum does it have? Momentum was what times what? Okay, so by the way, you might want your formula sheet in front of you. Just a thought, saying, good learning. Did I really need to tell you guys that? I guess I did. Oh, I weep. It's going to be 10 times 3. There's my mass times velocity. And I have something else moving. Bucket. What's the velocity of the bucket? Direction. South of east. Okay, I'm going to go like this. It's 40 degrees south of east, so 40 degrees south of east. And it has a momentum of 15 times 2.2. And this question wants to know the direction that the curling stone was moving before the collision. That's going to be this here. I don't know it. Wait a minute. How do I add two vectors together? If I draw these tip to tail, I should be able to find the direction of the resultant by doing some trig. Okay. So we're going to have this. 30 plus, can someone go 15 times 2.2 for me? 33, I think, but don't quote me on that. Is it? Almost an isosceles triangle. Now, this angle here was 40 degrees. How big is that angle there? Okay, 140 degrees. And looks like my resultant is this. Can I erase that so it's not quite so cluttered? Now, this question doesn't want me to find the resultant. It wants me to find the direction. It wants me to find theta. Can you already tell me, if that's which way my curling stone must have been moving initially, what of what? North of south, south of west, south of what? Okay, this is going to be south of east. Now I just need to find the degrees. Let's see. what I'm always looking for if I want to find an angle, if possible, it's nice if I can use the cosine law or the sine law, find a pair. Sine law is when you have a pair. I don't know those two, I don't know those two, I don't know those two. That's not going to work very well. I'm going to make this 140 a little smaller so that takes up a little less room. 140 degrees. I think what I'm going to have to do first is use the cosine law to find that. And then once I know that, I can go sine of this divided by x equals sine theta divided by 33 and go shift sign and find theta. So the cosine law, which is on your formula sheet. Do you remember the cosine law? Can you read it to me, Jesse? X squared equals 30 squared plus 33 squared minus 2 times 30 times 33 cosine of 140. This doesn't find you x. What does this find you? So please don't forget to square root. 30 squared plus 33 squared. The nice thing is you can type this in one line if you have a good calculator. Times, or minus 2 times 30 times 33 cosine of 140 square root. I get 59.21 for x. And now I have a pair. I know both of those. So I can say sine of 140 over the side across from it equals the sine of our mystery angle over the side across from it. That's the sine law, also on your formula sheet, by the way. Mike, how would I get the sine theta by itself here? What times what divided by what? Do the whole thing. So I'll give you a hint. 33. I'll give you another hint. Sine 140 divided by what? Do that on your calculator. Oh, this doesn't give you theta. What does this give you? Sine theta. How would I find theta at the very, very end? Inverse sine. And I get, oh, I bet you the answer is supposed to be, I bet you the answer they started out with to make this question up was exactly 21 degrees. Okay? So for momentum, for collisions, if they're straight and linear, just make sure you let to the right be positive and to the left be negative. When are they straight and linear? The ballistic pendulum, where you're firing a bullet into a block, that was a collision, and then a change in height. Oh, change in height, energy. Or we did the ones where the roller coaster rolled down the hill, crashed into another roller coaster, and then how high would they go? That was a nice linear collision as well, with the roller coaster stuck together. Circular motion. A blue ball, I don't know why they told me that it was blue. A ball is swung in a horizontal circle and completes a single rotation in 1.2 seconds. A 0.44 meter long cord makes an angle of 35 degrees with the vertical during the ball's motion. What's the centripetal acceleration? Okay. I'm thinking whenever they give me one of these ones at an angle, free body diagram, probably a triangle. Well, let's see. What are the forces acting on this sphere? Get the obvious ones. Gravity down. What else? Tension. What else? Nothing else. Wait a minute, it wants circular acceleration. Remember, circular acceleration, circular force, Mike, was the net force. It never actually appeared on a free body diagram. It's what you got when you added the forces together. How will I add these forces together? Well, how will I add vectors together? Draw them tip to tail. Now to do this, Sam, I always draw the easiest one first. What's the easiest force to draw here? I would go like this. I always draw the toughest force next. What's the toughest force? Tension. Now, I know not to go to there. I know not to stop there. How do I know I want to stop exactly right here? What path is this tracing out? A circle. Where must the net force be? Toward the... Has to be dead horizontal. Okay. What we're saying then, Sam, is this plus this plus this is what gives you your circular force, your centripetal force. Oh, we need an angle. Looks like right here is 35 degrees, right? So I'm pretty sure right here is 35 degrees. Gesundheit. They want me to find centripetal acceleration. Well, on my formula sheet, I have this. AC equals V squared over R, or it equals 4 pi squared R over T squared. They told me how long it takes to go around once. That's the period. I think I'm going to end up using this one here. So let's see. 4 pi squared R. Oh, I don't know the radius. Oh, I know the period though. What's the period? 1.2 squared. So you know what? I don't think I needed to necessarily draw this right now. I think I just need to figure out the radius, R. Now I drew this with you guys anyways because often they're asking you for a mass or a tension, and this will be your approach. Next time I'll read the question a little more carefully. How can I find what R is? Well, if I know that angle, opposite, adjacent, or hypotenuse in this triangle here. How about here? What's this? Hypotenuse. Sine 35 equals the radius divided by 0.44. Lee, could you get the R by itself? That's what I'll put right here. So actually, this question wasn't as bad as I thought. This was basically write down the equation and do some grade 9 trig. 4 times pi squared times 0.44 sine 35 divided by 1.2 squared. I get radius of 6.92 meters. Acceleration, Mr. Duick. What did I say, radius? Acceleration of 6.92 meters per second squared. I was going, this doesn't look right, because if that's that long, the radius can't be 6.92. That's why I was pausing there and going, what? I've done something silly. Okay? So other twists on this question, they might ask you to find the centripetal force or the mass, because now that you know the acceleration, if they told you the mass, you could find the centripetal force. Mass times acceleration. Or they could ask you to find the tension, because if you knew either one of those, you could find the tension using trig from this diagram. Electrostatics. Wrong button again. Come on, Mr. Duke. Electrostatics. Alpha particles with a mass of blah, 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 and a charge of blah, blah, blah are fired towards each other from a great distance. They're both positively charged. Will they attract or will they repel each other? Repel. If they each have a speed of that much to start with, what will be their minimum separation distance? I guess what we're saying is this. They each have kinetic energy. The closer they move together, the more that kinetic energy gets turned into electric potential energy. They're going to slow down, they're going to slow down. When they come to a stop for a split second, their minimum separation distance, that's when all of their kinetic energy has become electric potential energy. Then they'll start to repel each other. Does that make sense? All of our kinetic is going to become potential. Does that make sense? All of our initial kinetic is going to become electric potential. Kinetic energy, what's that? Half mv squared. Now we have two particles moving. Thankfully they're the same mass and the same speed, so I'm just going to go like this. 2 times a half mv squared. And conveniently, Christina, the halves cancel. I'll take that. Now, electrostatics. This was the one that had like 8 formulas that all looked identical. So you might want to very carefully look at your formula sheet and ask yourself, which of those is the potential energy between 2 point charges? I'll give you a hint. If it's point charges, it always has a K in it. Over R. Oh, are both charges the same? Do you mind, can I save myself some time and just do this? Because Q1 times Q2 is just Q squared, if they're the same. Less typing. What do they want me to find? Do you know the mass? They told you. Do you know the speed? They told you. Do you know K? It's not. What is that? It's a constant. It's on your sheet. 9 times 10 to the 9. Okay. Did they tell you the charge? Yep. Could you find R? In fact, I think this has suddenly become straight cross multiplying. I think the radius is going to be K Q squared all over M V squared. I'll assume you can type that. What other questions will they ask with electrostatics? Another classic one is 2 charges, finding the electric field between them, or the electric field at a certain location. Finding the voltage between them. That was what I asked you on your test. Okay. The key to remember, the tricky part with electrostatics unit was making sure you were finding what they wanted you to find. A number of you found the voltage when I asked for electric field, or found energy when I asked for electric field. And I know, Spencer, it's unfortunate because energy begins with an E and electric field begins with an E, and they use the letter E for both of them. EP for potential energy. That's why I always use capital P, capital E for potential energy. I know, but you just have to keep them straight. Oh, remember the first row in the formula sheet? Those were the vectors. We don't put the positives and negatives in. We said for forces and fields, we decide the direction. Like charges repel, unlike charges attract. Hey, what was the direction for electric field? Which way would a positive charge want to go if it could, if it was sitting right there? How big a positive charge? Such a small one that it didn't have its own electric field, because otherwise that would change the question. Okay. There was a part B to this question. I think the part B was using principles of physics right to explain question. I think it said something like, if the speed of each was doubled, what would happen to the separation distance using principles of physics right to explain? If that was doubled, you'd have a 4 coming out of there because it would be 2 squared. The separation distance would be 1/4 as big. Magnetic forces. I don't have a circuit here, sorry. A 0.75 meter metal rod is suspended as shown. A current of 13 amps then flows as indicated. Is the tension in the springs increased or decreased? So, it looks like, if I'm reading this properly, we are running a current this way, this way, this way. Which way is the current traveling in this bar? To the right. Which way is the magnetic field? So point your thumbs to the right, fingers out of the page. Which way is the force on this bar? Down. So will the tension in those springs increase or decrease? Okay. By how much does the tension change? I think it's going to change by the magnetic force. And I think the magnetic force is going to be... Did they tell me the magnetic field? Did they tell me the current? Did they tell me the length? Well, here's the question I need to ask, I guess. Does the current go just from here to here, or do I include the whole length? Pardon me? So the portion of this rod that's actually getting the current is just this stretch right here, because there's no reason for electrons or positive charges, the current, to flow in either of those directions. So 0.45. And the answer is, come on, 0.22 times 0.13 times 0.13, Mr. Dewitt, times 13 times 0.45, 1.29 newtons. Another magnetic forces question. So an 18 centimeter long metal rod of mass 35 grams is suspended from the ceiling with light wire. A uniform magnetic field is directed vertically upward. When there is a current in the rod, it swings outward as shown. So if it swings outward like this, which direction is the force acting on this current carrying rod? To the right. Point your palm to the right, because that's which way the force is. Which way is the magnetic field? Up. So can you figure out, is the current going from X to Y, or is the current going from Y to X? Which way is your thumb pointing? Right? So here's taking the right-hand rule in reverse. They're telling you the force is that way. Magnetic field is up the page, so my palm is pointing to the right. My thumb is pointing this way. I think from X to Y must be the direction of the current. So the direction, X to Y. Then the question is, how big? Anytime they give you something hanging at an angle, do a free body diagram. So here's my mass. What are the forces acting on it? Get the obvious ones. Gravity. Tension. And I guess the magnetic force is exactly to the right. Let's draw this as an equilibrium triangle. Draw the easiest one first, Sam. Gravity. Draw the toughest one next. Tension. I know, though, that magnetic force is exactly to the right, otherwise this wouldn't be hanging there. So I know to stop right there. And I think I can find magnetic force. This is 15 degrees right here. They did give me the mass, 35 grams, so 0.035. I know G. I think I can go opposite and adjacent. Which trig function links magnetic force and gravity? Tangent. In fact, we would say this: tangent of 15 equals opposite over adjacent. The magnetic force is going to be mg times the tan of 15. But wait a minute. They want me to find the direction of the current, the magnitude of the current. So I'm going to take this magnetic force, which is equal to mg tan of 15, and I'm going to recognize this is also BIL. Right? Get the I by itself. The current is going to be mg tan 15 divided by BL. Did they give me the mass? 35 grams, so 0.035. G is 9.8. Tan 15 divided by, did they give me the magnetic field? 0.22. Did they give me the length of this? Oh, 18 centimeters, so 0.18. 2.3 amps from X to Y. I said to you that on your written on Monday there's going to be some kind of a graph question. So here's an example of one. An experiment was performed on the surface of an asteroid. A mass was dropped from various heights and the time taken to fall was recorded. A says, plot a straight line graph of d versus t squared. They gave me d and t, so I guess I'll have to square these really quickly on my calculator. Takes a couple of seconds. 1.31 squared, 1.72. Thank you. $1.72. Oh, Lee, what's 0 squared? 1.56 squared. 2.43, 1.77 squared, 3.13, 2.05 squared, 4.20, 2.15 squared, 4.6. Okay, let's see if I can graph this. Goes through, oh, I need to pick a good scale. Let's see. My distance goes from 0 to 1.3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 squares, 1.3 meters. I bet you each square 0.1. 0.2, 0.4, 0.6, 0.8, 1, 1.2, 1.4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. I don't know. Each square be 0.2 maybe? 0.2, 0.4, 0.6, 0.8, 1. 0.2, 0.4, 0.6, 0.8, 2. 0.2, 0.4, 0.6, 0.8, 3. 0.2, 0.4, 0.6, 0.8, 4. Graph. Goes through 0, 0. 0.5, comma, 0.172, comma, 0.5. So there's 1.6. 1.7 goes through 0.5, about there. 2.43 goes through 0.7. 2.43 goes through 0.7, about there. 3.1 goes through 0.9. 3.1 goes through 0.9, about there. Getting roughly a straight line. 4.2 goes through 1.2. 4.2 goes through 1.2, about there. And 4.6 goes through 1.3. 4.2, 4.4, 4.6, 1.3, about, oh, Mr. Dewey, a little lower, about there. Try that again. No. Okay, freehand it, Mr. Duke. Use a ruler, but I can't put one on the screen. There's my line of best fit. B, find the slope. So slope is rise over run. If you're graphing a line, Megan, you have to use points from your line. I would not use this point right here because it's not on my line. I'll use, give me a nice point. How about right there? That looks like the rise is 1 over, the run is 3.4. Units, meters, seconds squared. Hey, what do you think the slope of this graph is if the units are meters over seconds squared? So when it asks me to find the acceleration due to gravity, I'm pretty sure that's just the slope. 1 divided by 3.4. I get 0.29 meters per second squared. What's the acceleration due to gravity on this very, very small asteroid? 0.29 meters per second squared. That's what I mean by giving you some kind of a graph to interpret. Okay? And then there's going to be some kind of a using principles of physics right to explain. So here's a circuitry question. It says, when checked with a voltmeter, an old 6-volt lantern battery shows the expected reading of 6 volts. However, the battery fails to light a low-resistance light bulb. Identify the property of the battery that must have changed as it aged and explain why this change to the property results in the bulb no longer lighting. I'm going to draw a little circuit. There's the battery. There's the bulb. Now, it's saying that it's finding 6 volts across this battery. So it's saying that before we hook it up, the voltmeter measures 6 volts. But as soon as we hook it up, nothing. Well, there's one more part to this battery. Remember, we said at the very end that we said batteries have an internal resistance. Normally, before you hook the battery up, since no current is flowing, you don't lose anything through here. But if this is measuring 6 volts from the battery, and we're getting 0 volts here, where must I be losing all my voltage? Right there. You know what must have changed? The internal resistance. I'm guessing some of the chemicals inside the battery have corroded or rusted, and so now the current can't travel through the battery unimpeded anymore. Explain why this changed. I would draw this circuit and I would say, using Kirchhoff's laws, 6 volts from battery, 0 volts in bulb, therefore 6 volts in internal resistance. Voltage is what times what? V equals what times what? V equals I little r. That's what we call the internal resistance. I don't think your current has changed. What's happened is this has increased. That's why old batteries stop working, even if you never use them. Okay. That's what I have for a quick review of the course. I hope that helped.
Investing in education is investing in the future of Cambodia.
More education, less poverty, and never more education, more poverty.
Cambodia has made substantial progress in education over the past 30 years. Despite impressive improvements in school infrastructure and accessibility, there was a major shortcoming.
The problem is the quality of education. So my job is to, make sure that Cambodians not just have access to education, but have quality education.
With a strong focus on quality, the government launched their third consecutive 5-year education strategy plan in 2009. Immediately recognized as being on the right track, the plan lacked the budget necessary to achieve its goals. So, in order to realize the government's vision, in 2011, UNICEF, EU and Sweden pooled $14.1 million and established the first phase of the Education Capacity Development Partnership Fund, or CDPF.
We are confident into the policies that the government is going to put in place in the education sector. What we are trying to do in Cambodia in the education sector is really to align our support.
It's the only fund of the sector that is entirely dedicated to building up the skills, knowledge and experience of the ministry, particularly in terms of planning and managing the education system, so schools, teachers, the education budget.
If there is no funding for some training, for some curriculum reform or review or teacher reform, then CDPF come in. This is the value of CDPF. It's complement the education budget.
The ministry takes the lead on the allocation of all funds. Together with the CDPF, they organise trainings at the national level on public financial management, planning, monitoring, accountability and education service delivery, to name a few. At the provincial level, the CDPF focuses on education planning. They do so within joint technical working groups, where they emphasise education data collection and learn to develop annual operational plans, among other things.
ផែនការប្រតិបត្តិនេះគឺយើងធ្វើរៀងរាល់ឆ្នាំគឺថាយើងបានដឹងថាឆ្នាំនេះយើងត្រូវធ្វើអ្វីខ្លះបាទត្រូវធ្វើអ្វីខ្លះហើយអស់ទឹកប្រាក់ប្រមាណហើយប្រភពថវិកាបានពីណា
In addition, CDPF allocated funds to acquire computers and motorbikes to increase communication and oversight.
ហើយតាមរយៈនៃម៉ូតូទុច្ចរិយយន្តដែលអង្គការដែលគម្រោង CDPF បានផ្ដល់ឲ្យនេះធ្វើឲ្យ DTMT យើងគឺថាបានប្រើជាមធ្យោបាយក្នុងការចុះពិនិត្យសាលារៀន
And at the local level, the CDPF and ministry are providing trainings to strengthen the capacity of school directors and increase the partnership between schools and their communities.
ក្រោយយើងប៉នហើយសិស្សដែលមករៀនមានការប្រែប្រួលអញ្ចេះដោយសារយើងមានកម្មវិធីចុះអប់រំតាមពុកម្ដាយនិងយើងតាមដានគាត់ពិតប្រាកដទៅឃើញថាការបោះបង់របស់សិស្សហ្នឹងវាមានការថយចុះ
To further improve schools across Cambodia, the Swedish government allotted a complimentary $22 million, and Phase 2 of the CDPF begins in 2015, investing an additional $11 million over the next 2 years. These investments in Cambodia's education system help to ensure that in every office and at every school, the ministry's employees will have the knowledge and training to deliver a quality education to each and every Cambodian child.
The outcome of the CPF is that after, say 5 years, the government will be able to do everything on its own.